Hi everyone, myself Navyatha working as Assistant Professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today I am going to discuss about intuitions for tree indexes and ISAM, Indexed Sequential Access Methods. And my overview of presentation includes, so what are the intuitions for tree indexes? That means the reason behind to choose tree file organizations. What is ISAM, Indexed Sequential Access Method? And structure of ISAM, that is Indexed Sequential Access Method. So let us discuss about the intuitions for tree indexes. So the tree indexes in DBMS are the data structures used to improve the efficiency of data retrieval. That is what we have discussed, two types of data structures, right? So in those two types, one of the indexes, one of the data structure that we use is nothing but tree based. Okay, next hash based, which we have discussed these two in our previous sessions. So what is the reason behind choosing the tree based indexes? Why? Because here we can improve the efficiency of data retrieval. That means as we consider that tree is arranged in a hierarchical manner, right? So the root node, if at all an element is less than, then it has to be placed in the left subtree. If at all it is greater than or equal to, it has to be placed in the right subtree. So in this manner we used to maintain all the nodes, right? So actual data will be there. For example, let us consider B plus tree, one of the tree file organizations, that is B plus tree. So in B plus tree we can have more number of children, and the actual data will be stored in the leaf nodes, only the leaf nodes, the internal nodes which acts as pointers to these leaf nodes. Okay, so what is the reason behind that one? So in this session, let us discuss the intuitions. They are based on hierarchical trees and allow for fast searching, insertion and deletion operations. So if at all we used to maintain some hierarchy, then we felt very easy to search, easy to insert and easy to delete also. For example, let us take here 50, okay, here 60, 40. Why? Because lesser elements must be placed here, 40, okay, and here 60, 20, 45, okay. Next, let us consider this one. If at all I want to search 45, then first initially I used to start with the root node, whether 45 is less than or greater than 50. It is less than 50, so I have to go for the left part of this one. Why? Because I won't search the right subtree. Why? Because in the initial stage itself we came to know that 45 is less than, so half of the search time will be reduced here itself, right? In that way we used to improve the efficiency while searching. Here are some of the intuitions, key insights about tree indexes. These are some of the intuitions. What is that one here? The first one is hierarchical structure, balanced nature. Why? What is the reason behind considering tree based indexing? Okay, so the first one is hierarchical in structure. We have to maintain hierarchy so that we can able to easily search, delete and insert the data items. Balanced in nature, so the tree is always balanced. Search efficiency, we can search the element in an easy and efficient manner within less time. Sequential access, one after the other we used to search, right? Next, insertion and deletion, which makes us very easy. Next, space versus time trade-off. So this is what the important thing. Space, it will take very large space to maintain number of nodes. Okay, the memory will be more. The memory required for storing the nodes will be more. Then versus time. Here, even though the memory, it takes a very huge amount of memory, even though the accessing speed or else whatever the data that we want to retrieve, the time will be reduced. That is what here. Okay, these are some of the intuitions by considering tree based indexes. Let us consider one by one in a brief manner. Hierarchical structure. Tree indexes are hierarchical, meaning data is organized in levels, that is root, internal nodes and leaf nodes. That is what the hierarchy. This hierarchy allows quick navigation. Okay, we can move from one node to another node quickly, making it easier to find the specific data. What is the intuition here? See the example. If at all I want to search for a word in a dictionary, and if at all there is no arrangement of alphabetical order, let us suppose, think, there is no arrangement of alphabetical order or anything, then we have to search from starting page itself, right? So, if at all the dictionary words has been arranged in alphabetical manner, then we can able to search that word from that letter it seems, right? So, think of looking for a word in the dictionary. Instead of flipping through every page, you follow an alphabetical order. Okay. Just why? Because the words are arranged in alphabetical order. We came to know that the words are arranged in alphabetical order. So, we can jump to that particular alphabet and we can search in those pages only. Okay. So, narrowing down to the section, then to the exact page. This is what. Next, what is balanced nature? So, let us consider B trees here. B trees or B plus trees also. Most tree indexes like B trees, B plus trees are balanced. All leaf nodes are at the same level, ensuring consistent performance for operations regardless of the size of the data set. Okay. So, what is intuition here? Let us consider library shelf. So, in the library shelf, books are arranged in a neat, right, one certain manner. So, where every book is placed neatly at the same height. That is what here balanced. This ensures equal access time to any book, preventing tall stacks that are harder to reach. The next one is third one, search efficiency. Logarithmic time. The height of the tree determines the number of steps required to find the record. That means number of levels. If at all the levels has been increased, the search time also obviously it will be increased if at all the node is the last node. Why? Because the actual data we need to search until the leaf node, right? So, in a balanced tree, this is the logarithmic relative to the number of records. What is the intuition here? It's like finding a contact in your phone, right? So, if the names are alphabetically sorted, each step eliminates half the time, half the remaining names, speeding up the process. This is also just like maintaining the contacts in alphabetical order, so that we can go to that particular alphabetic order. Then in that alphabet, the number of names whatever we want, we can able to search rather than searching all the names from starting. Next, sequential access. B plus trees are a special type of tree index where all data is stored in the leaf nodes. The actual data, whatever the data that we used to store, those data must be stored in the leaf nodes. And the leaf nodes are linked sequentially. So, this is what the representation, right? So, this is one node, this is another node, and these are the leaf nodes. Let us think these are the leaf nodes and each node is linked with one another. So, this is what the representation. And here we used to, if at all there is one key, we can have 2 pointers. If at all there are 2 keys, we have 3 pointers. That is, if at all we have m keys, then we must have m plus 1 pointers, okay, to point to the next node. This enables both efficient point queries and range queries. That means if at all we want to select a particular data, we can able to select. If at all we want to select a range of data, I want student details from 15 to 20, roll numbers 15 to 20, I can able to search in a easy and efficient manner. If at all I want roll number 15 data, then I can able to easily search. That is what here. So, imagine a row of houses where each house has number and they are connected by a path. Every house has a unique number and they are connected by a path. You can jump to a specific house or walk through them in an order. That is what the thing. Next, insertion and deletion. When a new records are inserted or old ones are deleted, tree indexes rebalance themselves to maintain optimal structure and performance. We used to replace the nodes also. If at all a nodes in the data in the nodes has been deleted, we can able to rearrange those nodes also. So, here picture a puzzle where pieces can be added or removed without breaking the overall picture. Pieces can be removed and added. We used to shuffle, right? The system recognizes itself to keep the flow intact. And last one is space versus time trade-off. So, tree index use extra storage to maintain the hierarchical structure, number of nodes. We have to store number of nodes. That means huge memory will be required, but saves time during data retrieval. What is it? It's like creating an address book. So this is what the intention, that is nothing but example, the reason behind. It takes time and effort to organize it, but finding a contact later is much faster. Even though it is a hectic task, but later on, it is very much faster to find out the particular contact. The next topic is ISAM. ISAM stands for Indexed Sequential Access Method. It is one of the tree-based file organization or tree-based structured index, right, method. So, it is a data access method used in DBMS to organize and retrieve data efficiently, just like B plus trees only. This is one of the tree-based indexing to organize and retrieve the data efficiently. It is designed for systems where data is mostly static. So, whatever the data is there, that will be static. It must not be changed with few updates or deletions. What are those updates? Here we can add one more nodes, and those nodes are nothing but we call here overflow pages that will be dealt in our structure. Okay. The data entries of ISAM index are in the leaf pages of the tree, and additional overflow pages change it to some leaf pages. So here what the data entries, initially whatever the data that we used to enter. Okay. So this is what 10, 20, 30, 40. The data will be represented with asterisk. The data will be represented. This is, if at all I used to represent asterisk symbol, then we have to note that this is what the actual data. So if just simply I used to represent here 10, 30, that means these are nothing but not the actual data. These are nothing but the pointers, points to that actual data that we used to remember here. Okay. And here we can have overflow pages. This overflow, this is what one page. Okay. One node. This is what we called as overflow page. If at all we don't have any space to insert, always remember the point. We have to insert data at the leaf nodes only. Okay. Why? Because actual data is present in the leaf nodes. So that is the reason we have to insert the data in the leaf nodes. So if at all there is no space in the leaf node, that means only one element we can store at a time for that particular node. Then where we have to keep, here again we have to consider one node, we have to add a link to this node, and this node is called as, this page is called as overflow page. So in this manner we can have overflow pages in this method. So how we can get overflow pages, how we can able to create ISAM structure, how we can able to insert the elements, delete the elements, that will be discussed with an example very clearly. But here in this session especially, I used to represent the basic structure of ISAM and what is the need and purpose of ISAM. Okay. The ISAM structure is completely static that allows records to be accessed both sequentially and randomly. This way we can access the records both sequential manner and in random manner. So it provides efficient support for both range and equality searches. If at all we want to search a particular item by considering some range of values, we can easily search. If at all I want to search a particular data item, that comes under equality search. See here what is range search, the example. Select name from student. This is what the column name, this is what the table name. Okay, this is what the table name. So select name from student where roll number greater than 15 and roll number lesser. This is what the range. From 15 to 40, I want the student names. That is what my intention. That is what we call as range selection. Some range I have mentioned here. Okay. What is equality search? So select name from student where roll number is equal to 15. Whatever the data that I want, just I used to point it out very clearly. That is what here? Roll number. Roll number is equal to 15. So it provides efficient support for these both kind of searches, range search and equality search. Next, what are the key features of ISAM? So here we have 4 main features. So that the first one is sequential and indexed access. Sequential and indexed access combines the benefits of sequential file access, that means fast range of queries, and indexed access, quick lookups for specific records. And data is stored in a sorted order for efficient searching. Whatever the data that you want to store, that must be stored in a sorted order. Okay, the initial step, that is we need to sort the given data elements first. Then only we must arrange. Okay. Next, the next feature is nothing but static. So ISAM creates a fixed structure of index and data files. It is always static. It is fixed. Any updates or deletions require creating overflow areas instead of restructuring the entire index. Whatever the updations will be done in the leaf pages until we must not touch the index, internal nodes. Next, the third one, we have two main components, that is primary index and overflow areas. So, a sparse index that map key ranges to the blocks data in the data file. So, here we have primary indexing. In the primary indexing concept, we have two types, dense and sparse. Dense and sparse indexing. So, what is dense indexing? Dense means for each and every key value, we used to point. We used to point a data bucket or a block. Okay. This is what we call as dense. What is sparse? Sparse means here, for example, 10. Okay. 10, 30. So, here this is what? From 10 to 20. Okay. Here from 31 to 40. Okay. Here from 50. In this way, some range of, here only for all the key elements, the data blocks has been mapped. Okay. But here, not for all the key values, only for some of the search keys. See here, we have skipped 20, right? So, for here, 10, 20, 30, 40, for each and every search key, we used to map. But in sparse index, only some range of elements must be mapped. That is what here we use. And separate storage of records that don't fit in their original block due to insertions. That means here those are called as overflow areas. So, if at all we want to insert a particular record in that leaf node, and that leaf node is if for example, it is filled, then where we have to insert that record? We need to create one more page, that means one more node, and we have to link that node. That is what here overflow area. Next, multi-level indexing. The primary index can be hierarchical, that is example with root, intermediate and leaf levels, allowing faster searches. So, these are the 4 key features of ISAM. Now, let us discuss how ISAM works. Firstly, we need to create index. Next, we need to retrieve the data. Next, we have to insert the data. If at all, we need to delete the data. Okay, these are the basic primary operations, how it works. Okay, now, let us discuss how to create an index. At the time of file creation, a primary index is built for quick access. We have to build a index. And next, for a specific query, the system first searches the index and then retrieves the corresponding data block. So, if at all I want the record 15, in the index table I used to search 15, and with the pointer's help, I can go to that particular block. Okay. Now, handling insertions. So, new records are stored in the overflow areas without modifying the original data file. Whatever the new records are there, they can be stored in the overflow pages. That too after the leaf node. This keeps the structure static but increases fragmentation. This is what? Right. Next, deletion. Records are marked as deleted but not removed immediately. If at all they are overflow pages, they can be removed. If at all they are leaf nodes or index, we must not remove them. This requires periodic recognition to clean up the files. This is what working. And how the nodes will be. Okay, what are the format of nodes now? Here we have two types, index pages and data pages. Index pages are also called as non-leaf nodes. Data pages are also called as leaf nodes. Why? Because the actual data is stored in the leaf nodes. So that is why data pages is also called as leaf nodes, and index pages means internal nodes which contains pointers. As we all know that index table which contains key value and pointer. Okay, key value and pointer. This pointer points to the block of memory or buckets. So this is what index table. So index pages are nothing but non-leaf nodes. So here, what is the index node? Every index node in ISAM contains the collection of search keys and a pointer. So like this. This is the structure for creating index node. These are nothing but the keys. Okay, key 1, key 2 up to km. Okay, these are nothing but the keys. For every key, we have two pointers, left and right. So if a node contains one element, so it has left pointer and right pointer. Why? Because the less than value contains left side and right pointer points to the right subtree. Okay. So if at all there are m keys, then how many pointers will be there? M plus 1. An extra pointer will be present. So if there are m such keys, m plus 1 pointers will be available. So each key serves as a separator for the contents of pages pointed to by its left and right pointers. Every key is separated, which is used to separate. That is what the basic structure of index page looks like. Okay. And have the data pages here. Data pages means what here? The leaf nodes. See here, you can see these are nothing but the leaf pages. These are nothing but the leaf pages, and these are all non-leaf nodes, which act as a pointers to these leaf nodes. And extra pages here. Okay, these are nothing but the overflow pages. These are nothing but the overflow pages, and these are nothing but what we called as leaf nodes or primary pages also. Actual data will be stored here and here. Okay, leaf pages contain data entries. So here the data entries, those are nothing but the actual records, are arranged in a sorted order by search key value. By considering the search key value, we can able to arrange the records in a sorted manner. Each data entry is denoted by, see, K asterisk symbol. So if at all asterisk symbol is there, then we can say that this is the actual data. This is what the actual record. Okay, that represents an actual data record associated with the search key value. So what we have discussed in this session? What we have discussed? We have discussed about what ISAM, and before that, so we have discussed about ISAM, and before that we have discussed about intuitions. Intuitions for tree indexes. Intuitions for tree indexes. That means what are the reasons behind to choose the tree based indexing. We have already seen about six intuitions, right? In the case of hierarchical manner, insertion, deletion, search, time versus. So these are different types of intuitions, and we have already seen about ISAM, that is indexed sequential access method, which is one of the tree based accessing, tree based data structure to access the files sequentially and randomly also. And we have seen the structure of ISAM. And in our next session, we used to consider one example, that means some of the data elements, and we used to create an ISAM tree, ISAM tree, and we used to insert the records, we used to delete the records. Okay. Thank you.